We made it, everybody. Hey, Calc BC, welcome to the last lesson in our Unit 3, 3.10, Volume with the Washer Method. If you take a look at the College Board's units, we're in Unit 8, as we have been, and this is our last two chunks of Unit 8. That's Lesson 11 and 12, Volume with the Washer Method, revolving around the X or Y axis and revolving around other axes. That's what we're going to be combining in today's lesson. There is one more lesson you see in College Board's Unit 8, the arc length of a smooth planar curve and distance traveled. Notice this is shaded in purple. It's BC only. So we're going to come back to that in a future unit. So we are going to start off here just looking at overview of these lessons. So lesson 11, volumes of solids of revolution around the X or Y axis whose cross sections are ring-shaped may be found using definite intervals with the washer method. And then the next lesson does the same thing, but around other axes. Okay, so that's what we're looking at today. I'm gonna show you the notes for a second and then do a demonstration. So let me switch over to that. All right, so here are our notes for today. You can see we can take the disk method and extend it to cover solids of revolution with a hole in the middle, and this is called the washer method. Let's say we have capital R, R of X is the outer radius, and lowercase r, R of X is the inner radius. And this is kind of where we take the area between two curves that we would have covered in a few lessons ago, and we extend it to volume. So we have this outer radius and this inner radius. So the outer radius is labeled in this diagram as r sub 0. That's like the r of x with the capital R. The r sub I, or r sub 1, I think it's r sub I. That's like the lowercase r of x. Well, if we have this area under this lower curve here and we revolve about this axis C, you can see based on this diagram over here that we've got kind of this shape where we've got this outer part revolved and then an inner revolution is kind of cut out of the shape. So there's a hole straight through the middle of this 3D shape. And if you look at just what's being formed here, this slice looks like a washer, if you're familiar with tools. And then that's why this is called the washer method, right? Because it's kind of like a washer that you would put on a screw. And so we've got an outer radius and an inner radius. So that's what we're working with here. I've got a real life wooden model to show you. So give me 1 second and we'll get this set up. All right, so we've got our diagram again on paper, and let's say that we are using this function y equals negative x squared plus 4. We're going to go from -2 all the way to 2 along the x-axis, and we're going to revolve this region about this vertical line. Okay, so I've got my model here of this 2D area on my drill. And as I kind of pull the trigger, you're going to see that we're going to revolve this whole thing around that vertical line. And as you do that, it's making kind of like this is one of those cake shapes, right? What is that? Like a pound cake or a bundt cake? Something like that. See if you can imagine that shape that this is forming as we revolve it, right? I'm sure somebody can correct me with what kind of cake that is. Anyway, what we're going to be doing here to make this is cutting this again into slices like we've been doing for several lessons, but let me pull this out of here. And let's stick this in instead. Okay. And imagine this. So we've got this slice, and you can see there's some extra metal wire on my tool here before it turns to represent that we've got that extra blank space there. So when I revolve this, you can see there's going to be a hole in the middle. And so the outer radius would be this upper bound, the distance between the upper bound and the dotted line. The inner radius is going to be this lower curve and the dotted line. And so we're going to have to subtract those two areas. I'm going to switch back to the notes to show you what I mean momentarily. All right, so here are the notes again. And you can see that what we're going to have to do here for the volume about a horizontal axis by washers, we're going to have the volume equals pi times the integral from a to b of the outer area squared minus the inner radius squared, rather. The outer radius squared minus the inner radius squared dx. And I wanted to show you, based on this diagram down here, what we're talking about. Think of this as one of the slices of this volume up here, right? This center slice right here. We've got our outer radius and our inner radius. So if we just wanted to find, if we were not even thinking about volume right now, we were just looking at this 2D shape and we wanted to find the volume of that shaded region. Let's say that this outer radius is 4 and the inner radius is 3. How would we do that? The area of the shaded region would have to be the overall circle's area, so pi times 4 squared, minus the central part, pi times 3 squared, right? Another way of writing that would be if we could factor out the pi and then write it as 4 squared minus 3 squared. And if we do that, we're going to get 16 minus 9, so we're going to end up with 7 pi. And we need to make a special note here that, make sure you write this down. We always need to remember that we square, for the washer method, well, to find the area here, we square before we subtract. Square before we subtract, right? Because if we subtract these two radii, 4 minus 3, then square, 1 squared is 1. So we'd have an answer of pi. But that region that's shaded here doesn't have an area of pi. It's the outer circle minus the inner circle. So it's pi times 4 squared minus pi times 3 squared. We can't just subtract and then do the area of a circle with the subtracted radius. We got to do all of the work. So what this volume formula does is for each slice, it accounts for the pi being factored out already, like we did in this second step here. And then we've got the outer radius squared minus the inner radius squared. Just like always, we can do the same thing in terms of y. If it's about a vertical axis, and it's going to be pi integral from a to b, r of y squared with a capital R minus r of y squared with a lowercase r. Okay, things to remember. This is the exact same from the previous lesson. The representative rectangle is always perpendicular to the axis of revolution. So up here in this, we've got these slices going this direction, and our axis of revolution is perpendicular to that. And I think that's really all we need to know to get to example 1. So down here in example 1, I really like that we have this figure here so we can visualize what we're actually doing for these first couple examples. The region bounded by the graphs of y equals x and y equals x squared, the curve, that region is revolved around the x-axis. Find the volume of the resulting solid. So you can see we've got this weird shaped 2D space within these two curves here, and we're revolving that about the x-axis. You can see this is the shape of what our result is. The outside looks like a cone, but then this lower curve in here is kind of cut out. So this dotted curve above and below the x-axis here showing that that's really the bounds of our volume. And you can see that there's this space in the middle that grows as we get closer to the edge. And so we've got to figure out what's the volume of that shape. We're going to use the formula from the top. So we're going to have the volume equals pi times the integral from a to b of some outer radius squared minus some inner radius squared dx. And so let's see what we got. We're going along our x-axis, and the intersection points are at 0 and at an x value of 1. So we're going to go from 0 to 1. The outer radius is going to be from the x-axis up to y equals x. So that can just be represented by x. The inner radius is this curve x squared, and it can be represented by going from the x-axis up to x squared, which can just be written as x squared. Okay, so we've got the outer radius squared minus the inner radius squared. It's like we're taking pi r squared minus pi r squared for the outer and the inner circles. And so let's start to calculate this. We're going to end up with pi times the integral from 0 to 1 of x squared minus x to the 4th dx. And then we're going to get pi times x cubed over 3 minus x to the 5th over 5 evaluated from 0 to 1. And so we'll get pi times 1 cubed over 3 minus 1 to the 5th over 5 minus 0, because that's what happens when we plug in 0 to both of those. So of 1/3 minus 1/5, which is 2/15 times pi. So we got 2 pi over 15. And that's the volume of this region. Okay, so that's example 1. Let's see what happens when we revolve about an axis that is not the x-axis in example 2. So the region bounded by the graphs of y equals x and y equals x squared, that's the exact same region from the first page, from example 1. Now we're going to revolve about the line y equals 2. So you can see instead of going about the x-axis and revolving down here, we're revolving up this time about the line y equals 2. So it's not going to be the same volume. We're revolving in a different direction about a different line. So find the volume of the resulting solid. So we're still revolving about a horizontal axis. So we're still going to be doing a integral with x's. And I wanted to take a second just to write out what is the outer radius and what is the inner radius. Let's think this through. The outer radius you can see is being marked on our picture here with this line segment right here. So we got to be able to write an expression that represents that, that space. And think about this like our upper curve minus our lower curve when we find the area between two curves. And so the upper bound is just the line y equals 2. The lower bound is this curve, which has a formula y equals x squared. So that is giving us our outer radius. The inner radius is this line segment right here. The top is at y equals 2. The bottom is the line y equals x. So you can see we've got an outer radius of 2 minus x squared, an inner radius of 2 minus x. And so this part can get really confusing. So it's always going to be helpful if you write out your radii first, then get to the formula. So the formula, just like before, pi times the integral from a to b of the outer area squared minus, I said area again, the outer radius squared minus the inner radius squared. So once again, we're going from x values of 0 to 1. Our outer radius was 2 minus x squared. The inner radius is 2 minus x. Okay, so we are going to now calculate this. And again, I would like to be able to do this by hand, which we can do, but it's going to be a little bit of work. So this is going to be foiling, and we get 4 minus 4x squared plus x to the fourth minus 4 minus 4x plus x squared dx. So then I'm going to switch the signs over here, and I'm going to combine like terms. What do we get? We have x to the fourth is the biggest. We have a negative 4x squared minus x squared. So we have minus 5x squared. And then we have plus 4x and 4 minus 4. So the constants go away. All right, now we can integrate. And we get pi times x to the fifth over 5 minus 5x cubed over 3 plus 4x squared over 2, which becomes 2x squared, evaluated from 0 to 1. So when I plug in 0, I'm going to get all zeros. So I only really have to plug in 1. So we get 1/5 minus 5/3 plus 2. And that equals 8 pi over 15. So that is the volume of this 3D solid. All right. There you go. Let's try example 3. What about if we revolve about a vertical axis, such as the y-axis? The region bounded by the graphs of y equals x and y equals x squared. Sound familiar? That's revolved around the vertical line, x equals -1. Find the volume of the resulting solid. All right, so this time we are revolving about a vertical axis, specifically the y-axis. So let's write out our outer and inner radii. Oh, you know what? I think I keep saying that we're revolving about the y-axis, but we're not. We're revolving about the vertical line, x equals -1. My apologies, I wasn't looking at the picture correctly. So we've got to go all the way from this curve to the vertical line, x equals -1 as our outer radius, and our inner radius goes from y equals x all the way to -1. We are doing this in terms of y, so we've got to solve each of these equations as x equals, and then in terms of y. I don't need to put the plus or minus here because I'm only looking at the part of the square root of y that's in the first quadrant. So that'll work. So our outer radius is going to go from root y all the way to -1. So to the right, we're at root y. To the left, we're at -1. So it's root y minus -1, which we could just write as root y plus 1. Oh, my pen is dying. Okay, I'm going to switch colors to blue. Root y plus 1. If we have our inner radius, it's going to be on the right bounded by x equals y, and on the left by the line x equals -1. So it's going to be y minus -1 or y plus 1. And you can see in this figure here what this is really looking like as we revolve it. But let's try to plug this in. So we got volume equals pi times the integral from a to b of the outer area or outer radius squared minus the inner radius squared. And so we are going on the y-axis from a value of 0 to 1. And our outer radius is going to be root y plus 1. And our inner radius is going to be y plus 1. Okay, so let's go one step further, see if we can do this by hand. We'll end up with, once we FOIL, we'll get y plus 2 root y plus 1. Over here, we'll get y squared plus 2y plus 1. So I'm going to distribute the negative. And what do we end up with here? We'll get negative y squared, y minus 2y, so minus y, and then plus 2 root y, and the 1 minus 1 cancel out. So then we can integrate. We'll end up with negative y cubed over 3 minus y squared over 2 plus, okay, so that's y to the 1/2, so it's going to be y to the 3/2 divided by 3 times 2, and there's already 2 there, so that becomes a 4. And that's evaluated from 0 to 1. Okay, so once again, when we plug in 0, they're all going to go away. So I'm really just worried about plugging in 1. So it's going to be negative 1/3 minus 1/2 plus 4/3. And when we combine all that, we're going to end up with pi over 2. Yeah, because it'd be 1 minus 1/2. Yep, pi over 2. There we go. All right, so that's the volume of that region. That brings us to example 4. If we finally get some new equations for our initial region. The region bounded by the graphs of y equals the square root of 4 minus x squared and y equals 1 over x is revolved around the vertical line x equals 3. Find the volume of the resulting solid. Okay, let's see what we can do here. So the first thing that I want to do is probably to sketch this. So I'm going to start off with my coordinate plane. And let's see, we've got the square root of 4 minus x squared. I know from experience that that's the top half of a circle with a radius 2. So I'm going to sketch that. That is y equals the square root of 4 minus x squared. And then I have y equals 1 over x. Okay, so I know that that is kind of curve in quadrant 1 and quadrant 3, but it's only going to intersect this other curve in quadrant 1. So I'm going to sketch that, and it looks like this. And so there's our intersecting region, our overlap, and that's revolved around the vertical line x equals 3. So that's going to be over here. That's what we're revolving around. And so if you can imagine, I don't know if I can get this purple to work well enough, but what that's doing is making, might be good if it's fainted a little bit, but it's making kind of like a circular, I don't know what type of shape that is, but some sort of circular volume that revolves this way. All right, so that's what we're working with. So we are revolving around a vertical line. That means we need to solve both of these equations for x equals to start. So let's do that first. So this one is going to be pretty simple. Y equals 1 over x is going to become x equals 1 over y. And for this one, we've got to solve for x equals. I'm going to square both sides. Subtract the 4. Multiply by -1, so I'll get positive 4 minus y squared equals positive x squared, and then square root. Technically, I just square rooted. I should have put a plus or minus, but I know based off of my graph that I only care about the part in the first quadrant, so I don't need the negative. I'm just going to use the plus. So let's write our two radii then, the outer and the inner. Okay, so this is interesting because our axis of revolution is to the right of our region. So we've got our outer radius, which goes from here to here, which you can barely see. I need to get new pens, but I don't want to kind of clog this up by writing everything in the same color. But our outer radius is from here to here. To write that radius, though, we still are going to start on the right side and then subtract the left side. So we're going to start with that axis of revolution, which is 3, and subtract this curve, which was y equals 1 over x, which we solve for x and put as 1 over y. And our inner radius is going to be from here to here. The top or the right bound of it is that 3 again. The left bound is this curve, which is the square root of 4 minus y squared. So we found the outer radius and the inner radius. And now we're going to set up the formula. So our volume is going to be pi times the integral from a to b of the outer radius squared minus the inner radius squared dy. And so we are going to plug these in. This is going from a y value. Interesting. Well, we care about where these regions intersect, right? So we care about this point and this point. So we got to figure out where on the y-axis are these points so that we can put the bounds of our integral. We can't plug in the middle though. It's going to be 3 minus 1 over y squared minus 3 minus 4 minus y squared like that. But we need the bounds of our integral. So this question is calculator active. I didn't say that beforehand, but now that you see this, I sure hope we don't have to integrate this by hand. Although it actually probably would be doable. I don't know. I think there's going to be something over here that's going to be ugly to try to integrate by hand. I don't think the u substitution is going to work out very well. So let's graph these two functions. And we're going to do the y equals versions because on my calculator, I'm not going to do x equals. So we got 4 minus x squared and 1 over x. And we need to find the intersection points, specifically in the first quadrant. That's the only place they do intersect. So we got this one, which is going to be 0.518, 1.932. That's that point up there, and then this point down here. I'm going to write it down here. Let's find it. So we got second trace, intersect down here. 1.932, 0.517. 0.518. Oh, that's funny. The x and the y just switched, which, you know, makes a lot of sense because we got 1 over x and we've got a circle over here. So it makes sense that they would be kind of opposite values. But anyway, okay, so we are interested specifically in integrating in terms of y. So we're going from a y value to a y value. So we got 0.518 to 1.932. And that just confirms that we're going to use the calculator to integrate this because I don't know how I would plug those in by hand. So if you go to your calculator, type this whole thing in, make sure you watch your parentheses. You are going to get approximately 8.731 rounding to 3 decimal places as usual in AP Calculus, and that is the volume of your 3D solid. All right, so that is how you do volume using the washer method. Hopefully that makes sense. Please let me know if you have any questions as always, and go ahead and try the worksheet, okay? Thanks very much. Have a great day.